All right, well, welcome to my lecture on estimation. So this is going to be an instance where the MLE does not equal the method of moments. Okay, and my example here is going to be f of x is going to be the uniform density on 1 over a, and it's going to be 0 else. And here is going to be 1 over a for 0x less than a. Okay, so notice the parameter a appears twice. That's our density. Okay, and this is our goal. Estimate the parameter a from data. Okay, and there's two methods. So the first method is going to be the method of moments. And the second method is going to be the maximum likelihood estimator. So let's do this example here. Okay, so method of moments says we first have data, and we're going to label this data x1 through x sub n. The second step is just to set the expected value of x equal to the average value of the data. So this is from the data. That's the average of the data. And E of x, since we have a density function, is just calculated by integral from 0 to a of x times f of x. And f of x is going to be 1 over a dx. That's equal to x bar. Okay, so if we anti-differentiate this, this is going to be 1/2 times x squared times 1 over a, evaluated at x equals 0 and x equals a. We set that equal to the average value. When x is equal to a, we're going to have a squared over 2 divided by 1 over a, and that is just going to be a over 2. And on the right-hand side, that's equal to x bar. So the estimate of a is twice the average value. That's our estimate. Okay. Now, let's do it with the other method, the maximum likelihood estimator. So our first step is just to have data, x1 through x sub n. And our second is to form the likelihood. That's going to be f of x1 with the unknown parameter times f of x sub 2 with the unknown parameter times f of x sub n with the unknown parameter. If I write down this density function, it's going to be 1 over a if x1 is less than a, and is going to be 0 else. Then it's going to be 1 over a, 0 else, if x2 is less than or equal to a. It keeps going like this until I get to x sub n. Okay, and if we look at this right here, this is not, this whole term, if any of these lie outside of the interval 0 to a, the entire thing is 0. And so what this means is that there are n copies of 1 over a, so a to the n. And that means that every single x sub I has to be less than a. So that means that the maximum, since every single one has to be less than or equal to a. Otherwise, we get a value of 0. And that's our likelihood function. And it's a likelihood function of the parameter a. We want to maximize the likelihood function. L of a based on the value of a. So the first thing I'm going to do, we will graph L of a. And if I'm going to graph it, it looks like L of a, that's the y value, and a is the x value here. And I'm graphing 1 over a to the n. Okay, so let's graph this. Okay, and I'm going to insert a value here. That's going to be the maximum of x sub I less than or equal to n. And this equation right here, it says it's going to be 0 if a is less than the maximum. So it's going to have a value right there. That's a really bad drawing, but I think it gets the idea. So it's going to have this value right here. Then at the maximum is going to have this value, and maybe I should draw it here. So it's going to have that value, and it's going to have this value right there. Then when a gets bigger than that maximum, it starts to decrease like that, because that's the graph that we have if a is greater than the maximum. So it looks like this thing right here, that's the max value. So the maximum occurs at A equals the max of the x sub I. And that is our estimator. So this is the MLE estimator. And note, this is not the same as the method of moments. Okay, so there you have it. There's the maximum likelihood estimate.